And then this afternoon we're going to do Hess's Law, which is another way of calculating enthalpy change. So when you're given these questions, then you're sort of looking at what am I given. Sometimes, like I said, it will be very explicit in a calorimeter, use Hess's Law. The one that trips people up is stoich. Okay, so it's not necessarily super obvious. It doesn't say using stoichiometry, etc. So if you took the worksheet, you'll notice there are many stoichiometry questions at the bottom, because even though it's really not that difficult, often it gives students a little bit of trouble. Okay? And then potential energy diagrams, which is a way to visualize what we're doing. So if you are asked to write a thermochemical equation, then that means that you are adding the energy value as a term in the balanced chemical equation. So it's either going to be a product or a reactant. And the implication is that, especially, it's easy to think of when you think of endothermic. Endothermic reactions absorb energy. So if the energy value is a reactant, then it's required for a reaction to occur, which makes sense. You have to put energy in, and then vice versa, exothermic. If the energy is a product, then you're going to get it out. You can use it, and we use these reactions all the time. We heat our homes, we drive our cars, we make our bodies work because we have reactions that release energy. Okay, so for endothermic, energy has to be absorbed by the reacting system. So the energy is required for a reaction to go or proceed. That means the delta H value is going to be a reactant. And you have to decide. It's not going to say in an endothermic reaction, etc., write the thermochemical equation. You have to, based on the information you're given, decide if it's endothermic. So a less obvious way is if it talks about absorbing or gaining energy, then it's endothermic. And then there are quantitative ways as well. So the delta H value is positive. It's a calorimeter question. The temperature of the surroundings decreases. I chose this type of reaction on purpose. We are going to, one of the topics 5.5 includes writing formation equations, but this one's simple. We're just forming water. Sometimes this will be like part D. Part A will say, if you have so much energy, what's the mass? Or it could be like using a calorimeter, find the delta H, and then it will say, is the reaction endo or exothermic? So you can do it based on the quantitative side of things. In this case, it just says the formation of water absorbs 285.5 kilojoules. So there's our clue that it's endothermic, okay? Whenever you write a thermochemical reaction, hopefully it goes without saying that it has to be balanced. We would never write a reaction that isn't balanced, right? So we are going to form water. And again, we're going to write a whole bunch of formation equations, but logically, if you're going to form water, what does it form from? Hydrogen and oxygen. And then you would balance it. So that is what you would have done before. When you're asked for a thermochemical equation, then you have to include the energy. Including the units, right? We don't just write random numbers usually. That is terrible handwriting. I will fix it. I only made it red to make it stand out. You don't have to do that, but if you like color, so this is a balanced thermochemical equation. The energy is on the reactant side. Why? Because it absorbs energy. So the reactants need this energy in order for the reaction to occur. And usually or often, we like practical applications of this. If you think about the formation of water, if it was an exothermic reaction or it didn't require energy, as humans, we would be doing this all the time, right? There's a water shortage. So the fact that the formation of water requires energy actually makes a lot of sense. That's why we can't just go walking around making water wherever we need it. We have to recycle and use it again, which is a problem when it's dirty and gross, right? So same thing with exothermic reactions. We often use combustion examples. It makes sense that the energy value is a product because we use reactions, we burn things to get energy from them, including the food we eat. We break it down, get the energy out, and our body, our cells use that energy to do work. Okay, so this slide says almost the same thing, except, of course, it's an exothermic now. So heat exits, or the reaction is going to produce energy. So the delta H value is a product, or it releases energy. You'll see those kinds of words. Okay, so the words release, reaction produces or releases energy, makes something exothermic. And, or you're given the delta H value is negative. The temperature of the surroundings gets warmer, so the reaction has released energy. So this can be difficult sometimes because if you read this question here, it sort of looks like this value is positive. However, it's really not, okay? Because they use the word releases, then you don't write a negative here. It's like, redundant. So you really have to be careful sometimes when you're interpreting a question, okay? So combustion is a classic exothermic reaction. There's lots of ways to tell. So in this question, we'll use the word releases. So it's exothermic. It does expect you to write the combustion reaction. So CO2 and H2O. So when you go to do these questions in the textbook, sometimes it doesn't say what the reaction is, and you have to write it and then make sure it's balanced. And then we want to include the energy. So now the energy value is going to be a product. And we are going to talk about this today, but this time now our units are given as molar enthalpy or kilojoules per mole. So that's part of stoichiometry today. So if it's written like this, kilojoules per mole, how many moles is it for? 1? Since it says here, combustion of methane, this energy value is the molar enthalpy of combustion of methane. So you have to check, what is methane's coefficient in the equation? 1. So we can just put the number as kilojoules. If it wasn't 1, then we would have to double it if it was, whatever. So balancing, and that's part of what we're going to do for Stoic, okay? Really, most of the time it is going to be 1 mole here. Okay, this coefficient will be 1. And when we talk about stoichiometry and you think about it logically, if you had a 2 here and you're saying per 1 mole and you had twice the amount, oh, well, that makes sense. We're going to get twice the energy, right? So it is logical once you're used to it. So we'll do that again. We'll talk about Stoic in the last part of this lesson. But most of the time, we're not out to trick you, okay? Usually it is 1. So usually it'll be fine. Okay. So potential energy diagrams are going to visualize the relative enthalpies of reactants and products and whether the reaction's endo or exothermic. So it's 50-50. It's either endothermic and you draw one shape, or it's exothermic and you draw the other shape. So again, you'll have to potentially decide, is it exo or endothermic, and then draw the appropriate diagram. So let's say you screw it up and you say it's endothermic, but it's actually exothermic, but then you draw the correct diagram. I don't take marks off over and over again, right? So if you carry your mistake through correctly, I'll still give you part marks. So don't give up, make a guess, because it's 50-50, endo or exo, and then just keep going. So we're going to show potential energy, because potential energy is the energy stored in chemical bonds. And of course, that's what we're talking about. When the bonds are broken, does that require a net absorption of energy, or is there a greater release of energy? And so when the potential energy is either stored in the bonds, like absorbed, or released, then we're going to visualize how the particles change. We're going to have to add one little thing from the next unit. We're going to talk about, we're going to call the energy absorbed that's required for any reaction to occur, we're going to call that activation energy, which we haven't done that yet, and we'll use that term again next unit. So the vertical axis, or like the Y, is potential energy, and then the horizontal is sometimes called time, sometimes called reaction progress, sometimes it's called reaction coordinates. And really all it's saying is, as time goes along, as reactants are changed to products. So the good news about these diagrams, they are totally, the shape is just generalized. You don't have to draw it to scale. We're not going to make appropriate intervals. You just have to make sure you have either the endothermic shape or the exothermic shape, and make sure I can tell that you know the difference. So that's all we care about. What's the shape of the curve? So the endothermic reactions, the reactants start with a little bit of energy, and they have to absorb energy to make the products. So if they are absorbing energy, then the products have more than the reactants did. And then vice versa. In exothermic, the reactants have a lot of energy, and then they release it, so the products have less. So I put more and less in quotations because, again, you're not going to put actual numbers. You don't have to worry about whether it's to scale or not. Okay, so if you printed the notes off, there should be two boxes. We're going to do endo in one and exo in the other. Okay, so you don't have to squish them. And then if you are writing it out, you can just keep going, obviously. did endo first before, we'll do endo first again. Okay, so again, you would be able to tell. So maybe you're given a reaction and it says A plus B plus kilojoules equals, or makes C, yield C. So then that's your clue, it's endothermic. Again, the same things that happened before. Maybe it's a calorimeter question, it said the temperature of the surroundings went down. Maybe the given delta H value was positive. So all of those ways that you can tell if something's endo or exothermic still apply here. We're just going to visualize it. Okay, so doesn't have to be perfect. We're going to do potential energy on the Y. Chemists are lazy. We love short forms. So you can even just write PE. I forget what your textbook uses, but I think they call it the reaction coordinate. Or progress. You can even write time. All three of those things are the same thing. It's basically as the reactants change into the products, really. Okay, so I'm just going to write a few little reminder notes, okay? So again, the reactants have to absorb energy, so they start with very little. How small? It doesn't really matter. However, you can't go to zero, okay? Don't defy the laws of physics that every particle has to stay in motion. So pick a spot, make a line. That was a terrible line, but that's fine. Okay, reactants. So you can either write what they are, or you can write the letter R for reactants. And then the reactants have to absorb energy. How much energy do they absorb? It doesn't really matter, okay? But make it obvious to me. Okay, so they absorb some energy. All right, and then, so now the products have more energy. How much more? Again, just make the difference between them obvious, okay? So one thing about reactions that we did talk about in 5.1, that every single reaction, every single time you break a bond, that requires energy, and every single time you make a new bond, that's going to release energy. But endothermic reactions, the net change in energy is absorption. The amount absorbed is greater than the amount released. So the way that we show that, it's not like an ever increasing graph or curve. What we're going to do is, so the reactants had to absorb some energy, but then there's a little bit of release and you make the products. So again, how big is the release? It doesn't really matter. Just don't make it all the way back down here, okay? And again, you can write the real product as you're given it, or you can just write P for product. If you want to write both, that's fine, but you don't have to. Okay, so there's two more things you have to label. So the one thing, like I talked about, is instead of just saying the amount of energy that the reactants have to absorb, we call that activation energy. And this, so it's literally like the energy required to activate a reaction. The only annoying thing is they use the symbol EA instead of AE, but it will be the same next unit and even in biology. Okay, so the activation energy, whether it's endo or exothermic, is the energy required by reactants to break bonds. So how do you show that in our picture? Or in our diagram, once you've drawn the shape, you start at the reactant line. Again, don't go to zero because nothing can have zero energy. So you start at the reactant line and go to the top of the peak and then just label it, okay? So you'll see when we do exothermic that that is going to look different. The activation energy should be much smaller. And then the last thing we have to label is enthalpy change. So I don't want to squish down here. So I'm just going to write what we're going to do over here. But if you have room down there, you can just keep going. Okay. Okay, so how do we show that? So the energy difference between the reactants and products. Here's the products, here's the reactants. So it's the height between them. Or distance, whatever makes the most sense to you. Yes. No, yes, for sure. I think your textbook uses this. I'm more like, I think use this and this, but it doesn't matter. It's basically just saying as the reaction goes along. Okay, so if you were going to do this on the test, it would say, slash quiz, it would say, draw and label a potential energy diagram. So you have to remember to label the axis, you have to do the appropriate shape, you have to do the reactants and products, and you have to label both of these. Okay, so it seems simple because it's 50-50. It's either endo or exothermic, and there are plenty of similarities, but they're annoying marks to lose. Okay, so please Just don't, oh, I think I got this. Make sure you know what labels you have to do, okay? Yes. No. No, you can write R, you can write P, whatever. Yes. Hurry. And when you come back, wash your hands. Thank you. Okay, we good? All right, so let's do EXO. Okay, so now the energy is a product, or the delta H value is negative, or it says release. Okay, so all those things are the same. Actually, I'll write action products. Let's see. Okay, so it says the reactants have a large amount of PE. How large is large? It doesn't matter, okay? So make sure I can see it. So again, whether you like A and B or R, remember all reactions have to absorb a little bit of energy when they break bonds. So we're gonna make a small hill, and then reactants, or the energy is released. Don't make the line go to zero. We don't want to say that that something has no energy, because that's not a thing. We can't do that. So again, how big should the difference be? Just make sure I can tell that you know that, okay? Reactants have a lot of energy, products do not. And then we have to label the same things, so choose the same colors you did before if you want. So it's the same thing. You start at the reactant line and go to the top of the peak for activation energy. So now you can see visually, is this a lot smaller than the endothermic? Yes, which makes sense. Endothermic reactions have to absorb energy. And then the delta H is the same. It's the height or the distance between the reactants and products. Yes. Yeah. 50-50. Yeah. Could we make them to scale and make it sure, but that's not really the point. We just want to visualize things like the activation energy is a lot smaller, which makes sense because endothermic reactions absorb, but exo release, that kind of thing. Because even in biology, when you'll talk about the energy changes in a reaction, they even want to be less quantitative than us. So just the general shape. Okay, so when you're asked to do stoichiometry for a reaction, like I said, it sort of does make sense. If you have a reaction with certain coefficients and certain amounts of energy, then in a different situation you have less or more, you want to be able to manipulate that energy value. So when we do Hess's law and when we do enthalpies of formation, the last lesson for this unit, they both have topics that have reactions that have reference values. Every single time you do the formation of water, it should take a characteristic amount of energy in a lab situation, right? So you can, we're going to use the back of your book. And this is not an exhaustive list, there are tons of reference values that we can manipulate and use in our situation. So for example, when we do the Hess Law Lab this afternoon, we're going to find the enthalpy of combustion for magnesium. So that's the one where you put the little strip and it makes the white light. You probably did it in grade 10, and your teacher always says, don't look at the white light, and everybody looks, right? So that reaction, imagine if we were going to burn magnesium in coffee cups. That's not a thing, right? We can't do that. But we can do the steps in the reaction, combine their enthalpies, and get the enthalpy for a completely different reaction. So and this last lab that we usually do normally is students get like 0.6% error, like super, super low, which everybody likes, right, when your reaction works. So the laws of thermodynamics really are easy to prove, and they like mathematically as well as visually. So people like that too. So if you're given a molar enthalpy or kilojoules per mole, which is a very common method of analyzing thermochemical data, but the coefficient is 2 or 2 moles, then the enthalpy would have to be doubled. We kind of already talked about that. If you have twice the amount of stuff, makes sense. You would release or absorb twice the amount of energy. So something like this, if you have 1 mole of carbon monoxide and then you half it, so I've taken 1 and divided by 2, except I don't know how to divide by 2 apparently. 2 divided by 2 is 1, not a half. And same thing here, please put in a half. So now we have half the amount, half the amount, half the amount. This is also going to be half. I chose half. You can choose literally anything. And that's when we learned about stoichiometry last year, that was the same sort of thing. It doesn't matter the amount of reactants you start with. You can do stoichiometry and predict the amount of products that should be produced. when we use stoichiometry, when we compare substances, you can't use, we always have to go back to moles, okay? So these questions often have 2 steps. So for the example that's, oh, sorry, Simon. Yep. Anything, yep. And then it makes it more universal, the reference value, right? In my lab, I have 10 grams. Lauren's lab, she has 25 grams, whatever, right? So we want, that's why even in organic, the IUPAC, right? We want universally applied chemical ideas so that no matter where you are, then you're getting the same results. Okay, so this example is good because this is sort of similar to what you would experience. So you're given a reaction, you have to draw the energy level diagram, you have to write the thermochemical equation, for example, which means that you have to be given enough information in order to determine whether it's endo or exothermic. So in this question, you're only given one piece of information, which is the delta H value, and it's negative. So what does that mean? Exo? So again, when you go to do A, let's say you're like, oh, I totally forget whether it's endo or exothermic, and you guess wrong, then, but you draw the potential energy diagram for an endothermic reaction, totally, you've labeled everything right, you would lose maybe a mark, maybe a half for the shape of the curve, but then you wouldn't lose marks down here or anywhere else. Okay, so just guess, don't leave the whole thing blank, because I'd love to give part marks, but if you don't write anything down anywhere, then I can't, right? Okay, so like I said, it says draw and label the potential energy diagram. So you guys have to make sure that you know the labels that have to go on there. And I apologize, those of you that printed it off. Again, if you want to try to write it down there, if you want more space so it's not super squished, do it on the back or whatever. When you do this, your endo and exothermic diagram, it's not like, you know, sometimes when you do graphs and your math teacher will be like, don't draw a small graph or whatever, your physics teacher. I just have to be able to tell. So as long as I can see your shape and all your labels, then it doesn't need to be enormous, okay? So exothermic, that means the reactants have a lot of energy, a little bit is absorbed to make the products. If you're into colors, you can use colors, but you don't have to. These are long, so I'm going to be like, I'm too lazy. So I'm just going to write R and P. And then top of the, for the reactant line, top of the peak is EA. The difference between the reactants and the products is delta H. Let's say you don't know how to do B and C. You could actually do D right now. You don't need information from B and D. I mean B and C. So try to, if you're totally 100%, you're not 100%. If you think you're like, I'm stumped, I don't know how to do this, do whatever you can, okay? Okay, so like I said, I think one of the reasons that stoichiometry questions are a little bit tricky is because it doesn't say using stoichiometry, all right? But what it's going to talk about is moles, or grams. And we call that's an amount, right? But it doesn't talk about, does it say in a calorimeter? No. Does it say the water gets warmer or colder? No. Okay, so this isn't a calorimeter question with amounts in it. All we have are the delta H value and a mole amount. So how much heat is released, or what's the enthalpy change? Those two things mean the same thing. When 3 moles of zinc sulfide reacts in excess oxygen. So the terminology excess oxygen, excess whatever, that's, you would have seen that in grade 11. So remember, we did a limiting reagent, right? And sometimes you were given 2 of the reactants. When it says excess oxygen, all that means is there's more than enough. You don't have to worry about that at all. We're going to focus on the zinc sulfide. So according to the reaction, how many moles of zinc sulfide, if all we had was this reaction, how many moles of zinc sulfide would react? 2. Whoever said that, how'd you know that? Yes, the coefficient is 2. Are 2 and 3 the same? No. So we need to figure out how much energy is going to be, in this case, released when now we have 3 moles of zinc. There are many ways to do this. I know that some of you had an unfortunate grade 11 experience, but we're just kind of going to try to move past that. So what I recommend that you do, and usually this is successful, is write the ratio, okay? So we are trying to find how much energy, if we don't know something, what do we commonly use? Like in math, whatever. Yeah, what letter? So we're looking for energy. It happens to be kilojoules. Usually, if you're using a reference value, just as an aside, usually the reference values are kilojoules, not like calorimeters that are usually joules, okay? Just so you know. We want to know how many kilojoules for 3 moles. I'm going to write the 0.0 so it looks exactly like the question. Obviously, that's not going to affect the math, but that's fine. And so now we've written kilojoules. On this side at the top, what has to go there? If I wrote kilojoules here, what has to go here? Kilojoules, and we only have 1 kilojoule value. And how many moles of zinc is that for? 2. Okay, so this side, as I've written it, there is other ways to do this. You don't have to do it the same way as me. On this side is from the question, how much heat for 3 moles? This is from the equation. This is the energy value for 2 moles of zinc sulfide. You do need to read the question carefully because the question could have said 3 moles of oxygen or zinc oxide or sulfur dioxide, and you want to make sure you use the correct coefficient on this side, okay? Which is kind of the beauty of moles, that you can compare anything as long as it's moles. So now you can cross multiply. You can do negative 878.2 divided by 2, and then multiply by 3 to solve for x, whatever you like best. We should keep the negative, right? Because that implies a release of energy. Before you even do the answer, think about the logic in it. Is 3 bigger than 2? Yes. So your answer should be bigger than this. You get a smaller answer, then you've done something wrong. So if you're already given moles, this question would probably be out of 2. It's not very much. I don't know if when we do the example, students think, oh, this is so easy. It's like grade 11. I can do this. And then they don't practice enough. Or I don't know what it is. But often, even though these aren't very many marks, often this can be the kind of question that students struggle with the most. I don't know if it's, again, if it's because it doesn't say use stoichiometry, blah, 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 like the other questions do. Okay, so the next question, part C, I'm obsessed with zinc sulfide. I don't know, I chose zinc sulfide again, but again, when you do stoichiometry, it could be anything. It could have been oxygen, could have been zinc oxide, it could have been sulfur dioxide. It doesn't have to be the same thing every single time. I'm gonna need a new. That was it. So in part C, you're given 223.9 grams of zinc sulfide. Can you put grams in a stoichiometric ratio? Can you compare grams and grams? Do we ever compare grams? No. We have to find moles, okay? So this part, that's like worth a mark. That would be like an extra mark to a stoichiometry question. You can trust, if you would like, trust me, the molar mass of zinc sulfide is 97.45. Zinc is 65.39, sulfur's 32.06. You just add them together. So when you write the quiz/the test, you're going to get a periodic table and any other reference materials that you need, okay? I'm just going to write moles ZNS again to emphasize I am obsessed with zinc sulfide. That's what's in the question. But now we're going to do the same thing. How much energy when you have 2.3 moles? What do we have in the question? Negative 878.2 for 2 moles. Again, 2.3 is bigger than 2. Not a lot bigger, but still bigger. Mhm. Yes. The only real times where it'd probably be in joules if it was like a super simple question or a calorimeter. Okay, so because I don't want to make a new slide, I'm gonna write up here. You guys can keep going or do whatever. So like I said about D, writing the thermochemical equation, you could have done that right away. You don't need any of this math because you're already given the skeleton part. You already decided it's exo. And I'm going to run out of room. Okay, so then you just write the energy as a product. So that's in the reaction. It's not separate. It's bad chemistry grammar to write minus. Being on the product side implies that it's exothermic. If you write minus, I won't take marks off, but you don't need to write the minus because it's on the product side, okay? But that's it. So you could have done D without doing B and C, okay? Yes. 878.2 kilojoules. Just the energy. Energy as a product. Then part E says molar enthalpy. Okay, so again, it's like you can do all the tough stuff, but then the stuff that's supposed to be easy. So molar enthalpy is probably only going to be at a 1 mark, but students often get so stressed about it. If you're doing molar enthalpy, then you want kilojoules for how many moles? 1. So often, if the coefficient's 1, then this is super straightforward. You can just write the answer. But I think I did zinc sulfide again. I did. I chose it especially because it's got a coefficient of 2. So some of you will recognize, oh, I just have to divide by 2 and that's going to get me the molar enthalpy. That's fine. Or if you're wanting to keep your stoichiometry questions all the same, then do the ratio, okay? It's just how many kilojoules for 1 mole. So basically all you're doing is dividing by 2, right? Some people like to have a sentence here.